Hi, I'm Hyunju Chang from Korea Research Institute of the Chemical Technology. Today, I'm going to talk about the data-driven research to find new thermoelectric materials. First of all, I'd like to thank NVIDIA for inviting me for this nice workshop. For the data-driven research, I would suggest the three key elements. We need big data and AI algorithm, which is appropriate to the material science, and we also need the domain knowledge. However, the data in material science usually have some limitations. Material data size is small and diverse because the various synthesis and the evaluation methods. So it's hard to build a big data. And also, it's difficult to including the bad experimental data, because in the public data, usually you can obtain from the literatures, such as the professional journals. The researcher published only champion data, so it's hard to get top result. So it's a major difference between the social data and research data. I'm going to talk about the thermoelectric materials today. So thermoelectricity is one of the direct energy conversion of heat into the electricity, or the electricity into the heat. Thermoelectric materials are known as the best eco-friendly energy harvesting materials. However, it's difficult to develop the new thermoelectric materials because of their thermoelectric property is the complex of the various physical properties. For the maximum efficiency of the electric conversion from heat to the electricity is determined by the figure of merit of the GT. The figure of merit GT is defined as like that. And then for the maximum efficiency, we need large electrical conductivity with the small thermal conductivity with the largest Seebeck coefficients. However, the most of the materials, the electrical conductivity and the thermal conductivity behave with similar trends. So it's quite difficult to find the maximum GT values. So we need, in this field, we need new research paradigms. So we have started from the data-driven research. In this case, we focused on the thin solenoid-based materials because thin solenoid-based materials could candidates for the high-temperature thermoelectric materials here. Globally, the 70% of heat which is generated in the process of using primary energy is wasted without being used. So high-temperature thermoelectric material like the thin solenoid can be earth-saving chemicals to recover the wasting heat into the electrical energies. This is the workflow of our data-driven search for the optimal doping element in the thin solenoid. First, we started from the systematic data generation and collection. And from using the collected data, we're gonna build the machine learning predictive borders. And with the machine learning borders, we screen the space of the chemical space. So then we can identify the dopant for the high GT materials. After the identification, so we have to validate that our ML prediction with experimental synthesis and the computational analysis. First of all, we have to think about how to collect the data. In general, the research data is stored in the personal computer, and then some measurement data from the various instruments is transferred into the PC using the USB, something like that. This kind of data is easily lost after the writing a paper or the graduations. So we have built the web-based data platform. One can use easily to upload files by drag and drops method, and then also one can easily share the result with the colleagues. Then this web-based data platform kept the dark result, so it's easy to leverage the data for the AI-based research later. Let me introduce our web-based data platform, T Explorer. This is a web page address which you can reach it. This kind of web-based data platform has some advantages because the web-based data platform can be used without installation. And also, it can be accessed from any device, even with a mobile phone. And then the collected data can be easily downloaded and managed using the API for building the ML machine learning models. The TA Explorer provides some kind of data searching functions from the periodic table or text-based search. The searched result is listed with this screen. And then it shows some data summary of the composition of the samples and the experimental method like that. When you click this sample ID, then you can see the more detailed data. This is one of the examples of the data visualization of the experimental data and calculation data. So you can compare the experimental data by just clicking the several samples. And also you can compare the calculated data from DFT calculation, such as the density of states or the band structures and so on. We generated experimental data and collected the experimental data from the Professor In Chang's group at the Seoul National University. They synthesized the 263 samples with 27 dopants based on the polycrystalline tin selenide. And they measured some electric properties, such as the electric conductivity and Seebeck coefficient and thermal conductivities. To build machine learning models, we have to clean the experimental data because experimental data is collected from the many students and there is many recording errors. So we carefully examine the data to find out the abnormal data point. So this is kind of essential to build good machine learning models in this stage. We also generated a computational data set using the DFT calculation from the WASP code. And then in this case, we built supercell with a single doping case. So there are three possible configurations of the tin substitute and selenide substitute and interstitial states. We took the electronic structures from the most stable structures from the three different configurations. To build the machine learning models, we have used three different kinds of feature sets. And also, we use gradient boosted regression tree method. Actually, we have tested several other machine learning algorithms, but XGBoost gives us the best result. And then we built the three separated predictive models to predict the electrical conductivity and the Seebeck coefficient and thermal conductivity. In this case, we have used three different descriptors groups to see the extrapolation effect. The machine learning is well known to have some limitation of the extrapolations. However, in the material science, we need extrapolation because we want to predict new material outside of the data sets. So in this case, we built the two different models to see that the extrapolation effect. First mode, we use data set excluding the vanadium doped data for training to predict the properties of vanadium doped data. So this case is one of the extrapolation. The second model, we used the data set with only one vanadium doped data for training to predict properties of vanadium doped data. So this can be called as interpolations. When we use just only basic information as a descriptor, which is including some elemental ratio of chemical formulas and some experimental conditions, as you can see that the extrapolation is much worse than the interpolations in this case. But after including the elemental properties and the electronic structures, extrapolation is improved very much like that. So at this point, we can say that including the electron structure descriptors can improve the extrapolation, the capability in these models. Here is the machine learning prediction of the GT values using the 3 different ML predictive models. Here we can get prediction models of GT with the R-square of 0.75 in the high temperature regions here. However, the machine learning doesn't consider the thermodynamic stability, but the thermodynamic stability is quite important in the realization of the materials. So we have calculated the TFT-based solubility limit for all the dopants like here. Then with the ML predictive models, we have screened 59 doping elements with various dopant ratios. So we have calculated GT values on the 2,802 candidates. With combining the ML prediction screening and the solubility limit screening, we can suggest the new dopants for the high GT thin selenide-based materials. This is our suggestion. We have suggested 5 different dopants, which leads to the GT max values over the 2.0. So then we can predict all the properties with respect to the temperatures of the 5 candidates. Actually, the 3 of the 5 candidates was already reported in the previous report of the cadmium doped and lead doped and germanium doped. Professor In Chang's group can synthesize the new yttrium doped thin selenide thermoelectric materials after our ML suggestions. And then we can compare their experimental measurement with the ML predictions. You can see the quite close curve between the real measurement and ML predictions. This is the conclusion of our data-driven research to find the new thin selenide-based thermoelectric materials. So we started from the systematic data generation and the building of predictive models and screened by the models, and we can suggest the new compounds for the thermoelectric application, and then that compounds is validated with the experiments. So we suggest the new material from the data-driven research. This work is recently published at the JAX, so you can see the more details from the paper. This is closing remarks of my talk. The experimental and calculation data can be easily collected with the web-based data platforms such as T-Explorer. And I want to emphasize on the calculation data can be a good features for the ML prediction for the data points outside the experimental data to overcome the extrapolation limits of the machine learning. So this is one of the, we suggested this kind of the data-driven research method is the one of the cutting-edge research strategy for designing the new materials. This work has been done mainly by Dr. Jin-Ho Im and Dr. Yari Yi and Hyunju Chang in my groups, and I would thank you for your attention.